1 second while we start the streaming.
We are live.
All right, we're live.
Cool.
All right, it's my pleasure. Hello, everyone, to have you all here today and to introduce Andreas Läuchli today, who's going to be talking about Floquet spectroscopies. Andreas, please go ahead.
Yeah, thank you very much, Adrian, and the others for inviting me, giving the opportunity to give my online seminar here. So I looked at previous speaker, and I thought perhaps this topic I'm going to talk now might resonate with the audience. And so what I'm going to present to you is a method we came up with, which has to do with this problem we think is quite challenging, namely to understand how quickly periodically driven quantum many-body systems actually heat up when you drive them with a periodic kind of a time-dependent Hamiltonian, which is periodic. And so the work I'm going to present is already out as a preprint on the archive. You can see the number here in November. And this is work which my PhD student, Artem Raksheyev, did in collaboration with me. And so the outline, let me see. The outline is that first I would like to present you just a little bit of motivation about why Floquet systems are interesting. I guess those of you working on that problem don't need that kind of motivation, but for those who are new to that activity, a brief introduction, and then I will formulate the question of why this heating is an issue and what we can do to actually analyze it, and then we will also show a few applications beyond what we have already done, where we think that this new approach, or at least what we believe is new approach, might enable to what kind of questions might be tackled with that. So Floquet matter is kind of a booming business, as some of you might know. So the question is basically if you have a quantum many-body system with a Hamiltonian which is not constant in time, but actually has a periodic time dependence, like indicated here with a period capital T and the time dependence here. And so these systems have been kind of investigated and shown to be able to engineer new effective Hamiltonians. And a particular nice feature is that these effective Hamiltonians actually turn out to have new properties which the system microscopically, let's say in a static setting, would not show. And so here I'm showing a small sketch from an interesting review article by Takashi Oka and Sota Kitamura, which appeared in Annual Review of Condensed Matter Physics, where you just in a very quick plot, you can see that different ideas like this Floquet theorem, Floquet picture, hectic Hamiltonians, you can combine them with quantum materials, which perhaps in equilibrium and in the static settings are not topological. And if you drive them in a clever way, it actually might be that you can generate topological band structures. And if you then also combine that with interaction, you might end up in exotic states, perhaps even fractional quantum Hall states and so on, and also see perhaps kind of dynamical phenomena which you cannot see in a static setting. And of course, another important platform beyond condensed matter physics are also systems like atomic gases in optical lattices, which you drive periodically. There's also an interesting review article here by Andre Eckhardt from a few years back. And here, this is a summary to the left of a few experimental kind of ideas what you can do. So by suitably shaking or tilting optical lattices in a time periodic manner, you can, for example, engineer a Haldane kind of or a Hofstadter type problem where you have a square lattice with a substantial amount of magnetic flux per plaquette, which you can engineer that way. And also if you combine this with interactions, or you can generate exotic, also possibly topological states of matter, which are hard to generate otherwise with kind of equilibrium or static Hamiltonians. And so that's all very kind of very nice, but often these kind of these ideas rely on kind of single particle properties. So if you kind of solve a non-interacting problem, you can engineer these kind of topological band structures. But then it turns out that once you include interactions and the system is not somehow fine-tuned or integrable in a particular sense, then it actually turns out that periodically driven system actually are prone to heating. And so these are results which go back to work by Achilles Lazaridis, Rodrich Mössners, and others from a few years back, and also Luca D'Alessio and Marcos Rigol wrote very influential papers where they kind of made clear that if you take a system which in a static setting is kind of a true many-body system with kind of which is chaotic, which is not non-integrable, and if you periodically drive that system at very long times, these systems will actually approach the physics of an infinitely hot system. And so to some extent, you could say, oh, this is very bad news, because this basically means that all kind of ergodic many-body system, if you drive them periodically, they end up to be boring, namely infinitely hot. And so that's not exactly what we want. But on the other hand, already in a few works later on, even though these kind of results, which I just quoted, are believed to be true, it actually turns out that in numerics, there are a few microscopic models. If you drive them periodically, for example, as a function of the driving frequency, they show actually quite interesting behavior. For example, here there's a paper by Haldar, Mössner, and Das, where here there's a certain, so this is a drive with where you actually modulate the amplitude of the drive, but what you can see is a rather abrupt change of an observable as a function of here the driving strength, and even though all these regimes should actually heat up, like here at small kind of amplitude, it heats up, which basically means at long time this observable is actually zero, but then there's kind of this threshold behavior. And there's another paper here by Heil, Hauge, and Zoller, where here there is the period of the drive, which is plotted on the x-axis, and you can also see a rather sharp kind of transition in the plotted quantities as a function of this here of the drive frequency or of the drive period, where it was actually, it looks a bit like that at small frequency the system is actually not heating up. And so the question which is there out a bit in these works is the question whether is there genuine kind of threshold behavior, so that actually there is a substantial difference if you change the parameter, like here on the one hand the driving amplitude or the driving frequency, or is this more kind of something which is tied to the particular way how the heating was diagnosed, because there are a number of ways to diagnose heating, and some of these approaches, I think there are the ones which are used here, are somehow looking at kind of at the eigenvectors, let's say, of the Floquet propagator, and if these eigenstates kind of most of them resemble the infinite temperature expectation, then it looks kind of like the system would heat up to infinite systems. And if they're not in that regime yet, then you will probably see something else. But so these works did not specifically address the question of how long does it take in time for these systems to actually heat up to infinite temperature, but they were more taking a fixed system size and asking, if I take this particular system size and I push it to infinite time, does it really heat up to infinite temperature or not? And so it seems that the question whether one can numerically reliably determine heating times accurately seems to be a somewhat challenging and also to some extent open question. And so as I list down there is some progress has been made in the last two years or so. and I would like to note work by Norm Yao's group and Marcos Rigol's group, who did both of them real-time simulations for relatively large kind of one-dimensional many-body systems, so spin chains or interacting fermion chains. And also in Yao's group, they used some kind of matrix product operator type technique to go to larger systems and longer time, but that relies on some kind of effective hydrodynamic type description. And another notable result which Marcos Rigol and his collaborators derived is kind of the Fermi golden rule approach, which I think in hindsight is relatively obvious. So what you do is that if you look at the perturbative limit, where you drive a system with a certain frequency, but only with a small amplitude of the drive, then if the energy transfer per cycle, per period is relatively small, then you can actually formulate this as a kind of a linear response problem, and then you can calculate or determine the heating rate from a Fermi golden rule. And in a paper, PRL in 2019, they actually did this for a particular system, and it turned out to work quite nicely. And another interesting or important result is also that based on some Lieb-Robinson arguments, you can actually also bound the heating rate or the heating time using analytical techniques. And so if you're driving a system with a drive, which actually is made of local pieces, of local terms, then actually if you're driving with a sufficiently high frequency, then the heating rate is exponentially small in the frequency, or otherwise the heating time is exponentially large in the frequency. So what is still left to be done, also illustrated by these results here, is that there is a robust and cheap method missing, which allows you to calculate, to determine heating times accurately, efficiently, and also in a robust way. So by not using very particular features of a model. And so that's now what we're going to do, and I will motivate our method by actually starting to look at the Floquet propagator. And so in order to go there, I would like to introduce a little bit of formalism. And so the setup we're looking at, as I said, we're interested in a quantum many-body system. So for the rest of the talk, we will basically work with a spin chain made of qubits, so spin kind of two-level systems, which are arranged in a one-dimensional way. And then the particular Floquet protocol is also a relatively simple one, which is a switching protocol, or it's also called a bang-bang protocol, where basically we're taking two different Hamiltonians, and Hamiltonian H plus and H minus, and for some amount of time within our Floquet period, we're applying H plus. So this one part of the Hamiltonian, and during the other part of the pulse, we're actually applying the other one. So there's an H plus and an H minus. And so if you build the temporal average over your period, that is called HA. That's basically 1/2 the sum of the two. And the one which actually has the square drive kind of pulse shape is HD. That's the drive Hamiltonian. So that's one way to see it, is that we're applying a square wave kind of perturbation on top of an average Hamiltonian. That's one way to see it, with a rather large amplitude. So it's in that sense not a small amplitude perturbation, but a rather large. But actually this particular choice we're using was actually motivated by one paper which attracted our interest. And that's actually, to some extent, this is motivated from a trotter-like protocol, where you have one type of operators for one part of the cycle and another set of operator for the other part of the period. And then you can write down your propagator, which propagates you over one period of your Floquet cycle. So that's the concatenation of a plus u part and the u minus one, where each of them is the exponential of e, so e to the minus I h plus times the half period tau in the first half period, and then it's e to the minus I h minus tau for the second part. And as you probably know, if you have a certain propagator like this u of tau, you can actually define something which is called the Floquet Hamiltonian, and that's basically this kind of the logarithm appropriately defined of u tau. You can actually call this logarithm the Floquet Hamiltonian, and so that's the kind of the operator which appears up here in the exponential if you take the logarithm of the product of these two ingredients. And so a lot of work has gone into actually determining the expression of H Floquet for different kind of H minus and H plus, and also as a function of tau. And there are ideas like the Baker-Campbell-Hausdorff or Magnus expansions which do that. And so these results are important to get an intuition, but they're not very important for what we're going to do now. But this is just to set the notation so that it's clear what we're talking about. And so as I said, we're looking at this particular protocol with the plus and the minus propagator, which we concatenate, and to give you specific choices for these H plus and H minus, so the two terms, kind of the Hamiltonians which appear for the first and the second half period. As I said, since this is motivated from some kind of a Trotter decomposition, say from quantum simulation or quantum circuits, so this is actually a relatively simple setup. So the H plus part is really just a paramagnet in X direction, so we call it capital X, and this is nothing else than just the sum over kind of spin 1/2 X operators on all the sides of our one-dimensional chain, and L denotes the number of sides in along our chain. And then the second part of the so the generator of the second half evolution is a sum of on the one hand of a longitudinal of a Z magnetic field, which is called capital Z, and a ZZ, some Ising type interaction among nearest neighbors along the chain, and we group all of these together. And note that here for the time being, there are no other free parameters. So we just choose somehow this particular combination when there's no variable hx or hc or j. So we just put them all with amplitudes 1. So that's a restriction, but it actually turns out that this is a relatively generic example. So if you, for example, look at the average Hamiltonian, the sum of the two, this is an Ising model with a longitudinal and a transverse field. And this is expected to be a chaotic Hamiltonian. You cannot solve it exactly. And at least for parameters which are not too far from this particular choice, people have also looked at level statistics for the average Hamiltonian. So this is believed to be a bona fide quantum chaotic or ergodic quantum many-body system in 1D. And so what we do now, which is also not yet very kind of original or has not been done before. But so what we plot now is that we choose different values of this half period tau. So that's an important parameter. So it's basically the inverse of the frequency. And so we have this propagator u. And what we now do is to plot the kind of the eigenvalues of the Floquet operator. So since u is a unitary operator, the eigenvalues lie on the unit circle. And what you now plot in this kind of colorful plot to the right are basically the phases corresponding to these unit circle eigenvalues. So on this axis, we plot kind of the theta, as you can see, the angles go from -pi to pi, so covering a range of 2 pi on the unit circle. And here on this axis, what we're plotting is our choice for tau. So if we're down here, we're looking at the system where the period is very short. And if you might make tau very, very large, like here, like pi or 2 pi, so that corresponds to a sizable period. And so what is shown here is that we have chosen a particular system size, which is not too large. So just perhaps like this is perhaps 6 or 8 spins. And we're going into a particular sector of our spin chain, because this protocol we're looking at, this is actually translation invariant. So there is no kind of site dependent coupling or anything. So our many-body Hilbert space for any kind of parameter still enjoys translation and actually also spatial reflection. So we're actually working in a subspace where we have taken these symmetries into account, like being translation invariant and also even under spatial parity. And so if you go in such a block, your Hamiltonian has a certain number of eigenvalues and the Floquet propagator has the same number of eigenvalues. And basically each of these lines is actually tracking a particular eigenvalue as a function of tau. So these are the lines. And the color code, which you can see, the color code actually corresponds to to the expectation value of this average Hamiltonian, this HA, which we defined before, which is basically 1/2 the sum of the two, in these Floquet eigenstates. And so at very short period, so at high frequency, it is known from Magnus expansions and or other kind of corresponding expansion that basically this Floquet Hamiltonian is basically the same as the average Hamiltonian. And furthermore, for this particular protocol here, you can actually demonstrate that that kind of the instantaneous expectation values of the Floquet eigenstates in the Floquet eigenstates of the average Hamiltonian is actually proportional to the slope of these lines if you take the derivative with respect to tau. So basically, in this plot, there's kind of redundant information. If you look at the line here, its slope with respect to tau, then the color is basically has the same meaning. And so one interesting aspect is that here for intermediate tau values like pi12, there is a lot of going on, and also the lines start to get more or less straight, and so being white, which corresponds to this energy density of about 0. But then if you go to a spatial value of tau, so in this particular Hamiltonian, you can actually see that all eigenvalues focus again into two particular values of theta. So that's a very specific feature. This is not generic, but it's actually worthwhile looking at the dynamics and the heating dynamics also in the vicinity of these points, because our method is actually able to give kind of clear-cut results here. And that's something where other methods have much more difficulty in actually producing heating times. But so that's kind of the arena we're talking about. And so a particular feature, which perhaps some of you have also already witnessed, is that in these plots, especially if you come from below, you see initially these are rays going out more or less straight. But because these eigenvalues of the Floquet propagator lie on a unit circle, then actually rays which start to the right, which are like high energy states in your kind of continuous time Hamiltonian, and the ground state, so the lowest energy state, they actually start to cross here. And at least on the scale which I have shown you, it really seems like a crossing, like the two states are not talking to each other. But actually that turns out not to be true. This is actually an avoided level crossing. And so I think we should, for pedagogic reason, we should actually look a bit more carefully what's actually happening here, because it will actually turn out that these are the seeds for energy non-conservation. Because what actually happens here, and so this is assumed just in that part of the plot you have seen previously. So what basically happens in this region here is that two eigenstates which of the Floquet operator, which actually in essence resemble very much still the eigenstates of the original average Hamiltonian, and they have very different energy because these are the states which are at the opposite end of the spectrum for this small Hilbert space. They cross at a particular tau value. And we will show later that we're able to resolve by how much they actually anti-cross. So there is a very small matrix element which couples the two states because they're not protected by any residual kind of symmetry or quantum number. So there's a small level crossing here. And if you just focus in your many-body Hilbert space just on the subspace of these two levels which cross, then you can basically map this on a kind of a Rabi problem where you have just a two-level system with kind of a detuning and with a kind of a Rabi flop a matrix elements, which is related to this gap size. And then you can see here, for example, we choose a few certain values of tau. You see that you need many digits because it's only changing in the last digits. And depending on in which one of these initial states you start, whether in the first or in the lower or in the upper state, and for example, you're exactly fine-tuned, then you can see that you're very slowly making a Rabi oscillation, basically. So like if you're in the ground state or in the initial ground state, you start and you're sitting exactly on top of the resonance, then very slowly your instantaneous state is like changing from the lowest state in your continuous time Hamiltonian to the highest and back. And since the two states have very different energies with respect to the average Hamiltonian, this is really like the seed of a energy non-conserving process. And if you have many of them and you're not coming back, then this is really the seed for a heating process. So this motivated us to actually somehow take this observation of a single Rabi oscillation, which by itself is not heating, it's just an oscillation, but to actually understand that this is the source of heating. And if we're able to scale up this information, assemble more and more of these crossings and resolve the gap size, the minimal gap size at this crossing more precisely, we believe we're able to translate this information into a quantity, into a heating rate or a heating time. And so that's basically what I would like to guide you through in the next few slides, to actually turn this observation, which is also not, I think we are not the first to observe that. I think people are aware that these crossings are actually the likely seed for many body heating in a flocky system, but I think it has not been tried before to convert that into a kind of a robust kind of numerical tool to estimate heating times accurately. And so, yeah, so that's basically the core question we would like to answer now, is that can we come up with a quantitative understanding of the heating dynamics based on a scaled up version of this analysis of the minimal gap size in this plot. And so what is the first tool which we then used is basically to program an automated gap finder. So as I said, we now restrict the Hamiltonian to the dynamically relevant sector, meaning here, for example, using translation invariant being in the zero momentum sector and the spatial parity even sector. And then, and so here we actually have a very small system. This is just a 3-side spin chain, so it's extremely small. But then you only have a very small number of eigenvalues here. And then we choose a certain range of tau, so of the half period, which you plot on that axis. And you can see here you only have like six eigenvalues here in this plot. And then what the computer basically does is that it calculates this small propagator for a very fine grid in tau and plots these curves. And then what the code does next is that it actually resolves kind of locations in tau where 2 of these eigenvalues have a local minimum, like their distance between the 2 lines is minimal. And when it's minimal, that's where basically there's one symbol plotted here, like here this black ellipse, or here the yellow square, the green square, and here also the blue ones. And so basically these graphical entities, they indicate where the code has found kind of a local minimum in the distance between adjacent eigenvalues. And so that's the original plot, but it's as you can see, it's a plot with much less eigenvalues than the one I used before. And then here, I think this part we can skip. This is just has to do where the crossings are in a kind of by counting in which line they occur. But the interesting plot is now on this side here. You can now see on the x-axis, that's what is the size of the minimal size of this avoided level crossing in kind of in the theta direction. And so here the black one is a relatively narrow. I think you can still see it if you go close to the screen. It's a visible anti-crossing, but it's relatively small. And so it appears here. And this is a logarithmic scale. So you can see that's so the vertical axis denotes the location of the plotting, like at what tau does it cross. So that's a bit more than 1.5 here. And on the the x-axis tells you what is the minimal size at this particular anti-crossing. And then on the other hand, the yellow and the green by eye, these are like massive repulsive, massive gaps. So on these logarithmic, they're much more to the right. And then the blue gaps, they are tiny, however. And on this logarithmic scale, you can see there are like 10, a bit more than 10 to the minus 3. And then this violet one is again quite a large avoided crossing. And so now this is really a tiny system. It's only L equals 3, but we find a few of these minimal gaps and their size. And what the idea is now is that we scale up system size, but still we're using system sizes where we can actually have a relatively fine grid in theta and where we can find all the eigenvalues. So which basically means from the computing side, we can only do matrices perhaps of a few thousand eigenvalues where we can diagonalize completely the propagator numerically and do that on a fine grid in theta. And so if you're using this spatial symmetry, as I said, we can typically do system sizes of perhaps 10 or 15 spins or something like that, because we have to do it a lot. But these are still rather small system sizes. And so what happens if you do that for the particular protocol we just said, and we're starting here to the left with L equals 6, and then L equals 8, 10, and 12. And so, and we basically make a scatter plot where we basically record each dot here, each point is one gap which has been found. And we plot it on the y-axis at the corresponding tau location. On the x-axis, we plot the recorded minimal gap size, and the color of the plots actually indicates what is the energy transfer at that particular crossing, because that's not directly related to the minimal gap. The energy transfer is an additional quantity. And so if you do that, you see from L equals 6, we get a rather sparse data, but it's already having a kind of a curious shape. And then if you go to L equals 8, you start to see there are more and more points, but they're looking more and more like a bent curve like that. And then you go to L equals 10 and to L equals 12. And for L equals 12, you can see there is already quite a lot of points. And so we have identified quite a lot of these avoided level crossings. But as they are right now, it still seems a relatively crowded plot. And there are also some regions which you can see you do not find on the color scale, namely some light gray regions and some dark gray regions. And I would like to explain to you why we have to deal with them kind of differently, because they denote some limitations of at least of the algorithm as it runs right now, but it turns out that these are not severe limitations. So let me discuss what they are. So the light gray, so these are basically the ones which appear here at very short periods. This has to do that there is this kind of kink here, and this is an artifact of the fact that we are using a finite resolution grid in our kind of first implementation of the algorithm, is that we're using a grid in the tau axis with a certain grid spacing. And once you can see that our gaps are of the order of 10 to the minus 6, which is really tiny, but at some point we're not able to resolve gaps which are smaller than this grid spacing because of obvious reasons, and we would have to refine the grid even further to resolve these gaps which are even tinier. But since, as it will turn out later, these gaps, which are very small, also give rise to very small heating rates, or meaning very long heating times, we don't think that this is a very important limitation right now, because we can still make that grid finer if we really want to resolve that even more precisely. But we just want to point out that one has to be careful about the resolution. And so here it was already quite fine, but still, like here, we cannot reliably resolve minimal gaps which are smaller than 10 to the minus 6, which by itself is already very small. On the other hand, there is also a statistical effect which one observes, because what is shown here as a dashed vertical line is actually just a naive estimate for the mean level spacing in that particular Hilbert space sector which you expect. The reason being, as I said, that these theta angles, they all have to be in the kind of in an energy Brillouin zone of the circle, which means all the eigenvalues have to fit in a 2 pi interval. And so basically, if your Hilbert space gets larger and larger, then the mean spacing between eigenvalues is just 2 pi divided by the number of eigenvalues which you have in your sector. And so this delta bar, that's precisely just this naive estimate. We take 2 pi and we divide it by the number of eigenvalues. And so what we observe is that actually as we increase system size, then this theta bar is going down, obviously, because the Hilbert space gets exponentially larger. And we realize here, especially here, that actually there is an accumulation in this tau range. There's an accumulation of eigenvalues which are basically piling up at the mean level spacing. And so and you can also see from the data, it's true that we do not record kind of gaps which are larger than the mean level spacing. And so it seems that once these our systems are large enough, our heating is such that the thetas, the spacings correspond to that. We're having we're losing some dynamical information. Now here on this slide, this might look like a bad issue, but actually it turns out that this is the region where the system thermalizes so rapidly that we don't need our sophisticated methods. Even small size real-time dynamics will immediately tell you that the system is heating very rapidly. And so this is actually not the regime of interest to our method, because this can be done with a lot of cheap other methods. So that's not the domain of interest. But where our method really seems to work quite nicely is this regime where the gaps are kind of are few, so they're not, the level crossings are not many, but we can resolve them accurately. And that's basically the regime where we're able to track the large heating times, which are not amenable, actually, which you cannot extract from real-time simulations. And you can also see on the other side, there is also here this wing going down with the light green here, where the system is heating and where the heating, or at least where the angles are also going down. And the last kind of imperfection, if you wish, is the yellow region. So you can see as you make systems larger, there are kind of also gaps showing up, which our method resolves, but where the corresponding energy transfer, which is extracted, is actually turned out to be 0. And so this is on the scale, as you can see, this is yellow corresponds to 0 energy transfer. And so they were these kind of level crossings are kind of fake. I mean, there are real kind of minima according to how we define it, but it will turn out that they do not contribute to the actual heating process. So let us now, so I mean, now it might look a bit like this is a very limited approach, but now that we...
Sorry, could I pause you there, Andreas?
Yeah, of course.
So what is the important message here? I guess there's a lot of detail in these plots, but what should I focus on as, you know, the relevant piece that's controlling the heating in the system, which I think is what you're trying to get at. Is that correct?
Yeah. So right now, I think what I want to convey here first is that actually there is structure in this kind of large mess. I mean, if you go back, say to this plot, I don't know whether while looking at this plot, it was kind of obvious that you could extract something quantitative. So we think we were a little bit brave to really just go ahead and track all these level crossings. So like these points we get, they're basically obtained from all these kind of mutual crossing of these lines, resolve what is their minimal gap, and we accumulate that data. Mm-hmm. And so basically in these plots, which I've shown you, I show you that there is some structure. Now let's discuss what we observe. That's not immediately a heating formula yet, but I will come to that. But there is actually also, there are some things like for example, on this side that you, at very high frequency, that you don't get any crossings. That's something which people have observed before. That kind of, if your frequency is large enough, so that the two states, which are at the opposite end of your finite size many-body spectrum, do not have kind of a transition frequency from the Floquet drive which connects them, there is kind of no heating on that finite system size. So basically for a certain frequency, you always have to go to a large enough system size in order to observe heating. And that's also something which you can read off from these plots. But I think the important part is basically that at least on this wing, which I hope you can see my mouse pointer, this wing and this wing, this is the important part where we will be able to get quantitatively accurate heating, which we will match with two other methods where our approach turns out. And then this limitation here is resolution, but this can be dealt with. And I think the other thing, which is a bit, how should I say, requires a bit more care in explaining is something is that you see there's some kind of dichotomy in how you detect heating. Like I said before, there were these results where people were using kind of long time properties of a finite system to decide whether the system would heat or not. And what I'm kind of advocating in the end, even though I didn't spell it out right now, is that actually in this regime, which is the gray regime, that's actually the regime where we believe that the eigenfunctions of the Floquet propagator, which give to this spectrum in this gray regime, that's the regime where the eigenfunctions already look like infinite temperature. So if you go ahead and look at all the eigenfunctions, you will find that the system basically thermalizes to infinite temperature for that very system size. And that part out there, where we were resolving avoided level crossings, which are much smaller than the statistical level spacing, that's actually where our method really is able to pick the events which lead to heating and which will give you the heating time, even though if you do, for example, some random matrix diagnostic for heating, you will not find heating in this regime. So I think what we pretend is clever because we're looking for the avoided crossings. We realize that they were responsible for heating, and we're able to detect heating and predict heating times, even though not the entire Hilbert space is yet on this very same system size is kind of heating up, but we're able to extract the relevant information which is responsible for the heating and which will heat even in larger systems with the same rate. So admittedly, it's a bit complex, but I think it's important that there are like different regimes where, and that I think that our method works precisely in this regime, which is hard to address using, for example, real-time simulations, because I think the system sizes you would been able to treat for these very large heating times, as will turn out, is very difficult. But we can get it from L equals 12, which I think is quite an achievement.
Mm-hmm. Okay, great. Now that clarifies it a lot. Thank you.
And so now is the question, how do we convert these data sets, which I just told you, in heating times? And actually something which admittedly helped us in somehow converting it is that actually at large frequency, meaning small periods tau, there's a close connection of our approach to the Fermi golden rule. So the reason is basically that in the Fermi golden rule, like in very simple terms, what you do is that you take the eigenfunction of the average Hamiltonian, and then what you calculate is basically you need matrix elements of the drive Hamiltonian in the eigenbasis of the average Hamiltonian. And on the other hand, if you're working in the same regime in our approach, then it actually turns out that the quantity which controls the minimal gap size we're reporting is precisely the matrix element of the drive part of the Hamiltonian. And basically this plot here, without a lot of explanation, basically shows you that the crosses are values which our gap finder technique reports. And these boxes here are the matrix elements of the drive part of the Floquet protocol in the other eigenbases. And the fact that apart from very small ones, there's very good agreement basically means that the ingredients which we detect from our minimal gaps and what you would do in a Fermi golden rule calculation, they really match very well. And that's in a regime where the Fermi golden rule is very well controlled because we modify the drive such that it actually has a small amplitude. So we're really in a perturbation theory regime. And that's where the Fermi golden rule is really kind of very accurate. But our approach, since it does not really require perturbation theory to actually find the gaps, this is a kind of a purely computational tool which does not rely on perturbation theory. We're actually able to resolve the gaps even when the Fermi golden rule is not applicable. But using the connection in the regime where Fermi golden rule is applicable, we're actually able to conjecture or propose a formula for the heating rate in our method. And so and this is kind of the details I don't want to go through now, but basically I can tell you that the formula looks something like here. So E dot is the heating time, so the change of the average energy per cycle. Omega is kind of the driving frequency, so like 2 pi divided by the period. And then you have a sum here which enters, and the sum goes over all crossings. So C is the number of crossings. And so this basically means all the data points which I have shown you before, we go over all of them. And for each crossing has basically 3 informations which come here. So one is the minimal gap size. So that's this delta C. So that's the x-axis in all these plots. Tau C, TC, that's like the period. So that's basically 2 times tau at the crossing squared. And delta EC, that's basically information which is contained in its color, is by how much energy difference is there in the 2 levels which actually cross. And so that's all this information which you might remember was in this plot. And so we just have to sum them up in an appropriate way for a certain frequency. And we also have to regulate that delta functions in order to make sure that we're operating at the right frequency. And so, but these kind of orange shaded quantities are quantities which we get. And if you apply this formula in the Fermi golden rule regime, the 2 formulas really match. But what we basically take is that we gauge our formula in the Fermi golden rule regime. And then since the crossing data is also non-perturbatively defined, we can extend that formula also in the non-perturbative regime and get heating times out. And so,
Andreas, I'd like to ask a question. When you do this sum, so the gap distributions looked rather broad, even on a log scale. So when you do this sum, does it end up being dominated by a very small number of crossings? Have you looked at that?
Yeah, I think we can see later, I mean, just on the following slide, basically it actually turns out that, for example, here where you can still distinguish the crossings by eye, because this is not a histogram, this is really a scatter plot. So once you go to larger systems, one should actually bin the data probably to represent it better. But it actually turns out that probably the states on the edge here are the ones which dominate the sum.
Yeah, I'm just wondering if you assessed whether it's just an order 1 number of states or how many states. Have you asked that question, or maybe not yet?
No, I don't think I have asked that question precisely. But I think we can probably bin the data, and then the density of states enters in some way. No, I mean there are some density of states aspects hidden if you want to really scale that up to larger systems. There are some density of states questions which appear, like how many crossings do you actually detect? Does this have to do with like the density of states or squared of the level of how many crossings you would actually expect? But I think I don't have a very precise answer to your question.
Thanks.
And so now comes the test, basically. So you would like to compare how these inexpensive predictions, inexpensive in the sense that even L equals 12, which we have shown here, are relatively small matrix sizes. Okay, we have to diagonalize them a lot, but the matrix sizes are quite small, so you can do that on a laptop or a small workstation. So you don't need a supercomputer to do this simulation. So that's why I call them inexpensive. I would like to compare them to relatively expensive large-scale real-time simulations, and then also to other predictions. So let me now briefly mention the real-time simulations. So we're not the first ones to do them, but what we do here is to push system sizes up to 28 spins. And that's in the space with using periodic boundary conditions and these spatial symmetries which are in the problem. And then we simulate up to 10,000 flock cycles, which is relatively long. And this is just to show you the finite size dependence of this particular protocol for a particular value of tau of this half period of our protocol. And so you can see is that if you take L equals 16, which is not a small system, it's already larger than the ones we analyze, you can see, and I should also mention what I plot here, is that basically I take the initial energy, that's Q0, because I start in a particular initial state, which is not the zero energy state, meaning it's not in the middle of the spectrum, does not correspond to an energy density which corresponds to infinite temperature, but it's a finite distance away. And then I measure the energy after a particular cycle, and that I divide it by the initial energy. And since for this particular convention of Hamiltonian, infinite temperature basically means, since it's written in Pauli's, or that basically infinite temperature means that the energy should go to zero in these things. So if I plot this quantity, if this quantity goes to zero, that is a proxy for telling you that the system heats up to infinite temperature. But anyway, but if I do this same experiment for L equals 16, and I go to 10,000 cycles, you can see that indeed the initial kind of energy relaxes a little bit, but then it hovers around of a value of 0.1. So it's still quite a bit away from infinite temperature. But if you take the very same initial product state and you with the same frequency, but you go to 20 spins, then it starts to relax a bit more, and then it hovers roughly an order of magnitude smaller. And then if you push to 24, then it goes down even a bit further, and L equals 28. Okay, there's an even more pronounced, also here, roughly exponential relaxation, and then the noise level is even smaller. But you can clearly see that if you would, for example, look at the kind of the steady state for L equals 16, this has still quite a large remnant energy. This does not really correspond to infinite temperature. So in these real-time simulations, really important to go to very large system sizes if you really want to get the heating under control, and also if you want to accurately look at the dynamics in real time. If you want to fit an exponential, so a heating rate or an inverse of it, the heating time, you really need to invest quite a bit of resources to get that nicely converged. But here, for this particular value of tau, I think we have achieved that more or less, because I think this here, you can see that the green and the blue curves are roughly on top of each other. So that seems to be more or less under control. And then what we do, just as an exercise also, is to actually start with different states, like with the one which is a state which is polarized in minus x spin direction, in minus c, a superposition of Néel states, plus x or whatever. And you can see they have I mean, in detail, they have a bit the different relaxation dynamics, but if you fit the late time result with an exponential, and you get some heating times and you plot them on a logarithmic scale, that's basically what you get. So here on the x-axis, we plot the tau, so the half period of our protocol, and these different colors are somehow different initial states. And even though they differ by even some non-negligible factor, like a factor 10 or so, but you can see the overall trend and how steep the heating time shoots up as we lower tau. That's actually something which does not depend too much on the initial state. So in that sense, we should not worry about particular details of a particular initial state, but the heating kind of is mostly explained by tau, and not so much by which initial state we actually start. And then here in this shaded regime, the heating dynamics is actually so fast that we didn't really bother extracting a heating time because it's so short. And then on the other side, actually, if tau gets larger here in units of pi, then actually the heating time shoots up a bit. And you can see, since we're only simulating about 10,000 cycles, because that's already quite expensive, we actually limited to heating times of about 10 to the 4 in these real-time numerics. But this data seems to be converged in system size and also not being too much kind of initial state dependent. So let's now compare this with our kind of formula, which we wrote down based on this crossing formula. And so this is the overall plot. So it's represented a bit different. It's a bit crowded. So let me highlight the different ingredients. So initially, these gray symbols, the circle, square, and the diamond, this is basically the same real-time data I have just shown you. So there is real-time data shown here and on that front. And you can see the heating time in cycles changes about several orders of magnitudes, perhaps from roughly 10 to the 1 to about 10 to the 4 in this range here. Okay, it's just the same data. Then the full curves with various colors, this is now really the data which we have obtained from our avoided level crossing spectroscopy formula. And they actually, we show them for different system sizes. And you see, we just use system sizes L equals 6, 8, 10, and up to 12. And they get, especially for the larger system sizes, we get relatively smooth curves which have a clear very sharp tau dependence, and where actually we seem to to be able to predict heating times of like 10 to the 7 here in this range, and also on that side, which are very large, but they seem to be converged in system size. If you drop just the tiny L equals 6, and these curves actually look quite on top of one another. And then finally, since we mentioned it, there's also a Fermi golden rule treatment following this work by Marcus Rigol and his collaborators. And so that's this red dashed line. And actually at small, at high frequency, at small tau, you can see the curves really lie basically on top of each other, which is not so much of a surprise. We gauged it such that they kind of correspond to each other. But if you make our tau, so the half period larger and larger, you start to see that the Fermi golden rule is not describing the actual dynamics of our resistor anymore. And what happens in this particular problem is that there's something like a discrete time crystal on the other side as we approach pi here. And our approach is actually able to see that, that shoulder so that the heating rate is going down, or the heating time is going up, which is clearly in the real-time dynamics, and our method can see it, whereas the Fermi golden rule is kind of blind to this phenomenon. And so I think that's a clear advantage of our method, and also the fact that the real-time dynamics and our approach matches in the regime where both are available, I think really validates our kind of inexpensive and, we think, flexible approach. And so I think that the summary on that is that there's a very good agreement between our spectroscopic formula and the real-time dynamics, where the later data is available. And I think it's impressive, at least to me, that we're able to predict heating times up to 10 to the 7 cycles from smallish L equals 6 to 12 systems. So it really seems that focusing on the avoided level crossings seems to be the right approach to figure out heating dynamics. Now, in systems where you're effectively in the Fermi golden rule regime, our method does not really add new value, and that's basically on this shoulder here. Fermi golden rule does the job already very, very well, so there's not much to improve, but we agree. But here in this particular model, where there are other, there's another dynamics going on, Fermi golden rule is oblivious to it, and but our approach can see it. And so, yeah, I would like to advertise that this avoided level spectroscopy seems like a flexible and robust method to determine heating times. And now, as an outlook, since I guess I'm coming to an end, we think that this approach actually has also potential in other in other open problems. So what is next? So as I said, so far we consider the model which has no additional symmetry or conserved quantities other than this translation and spatial reflection symmetry. But in the spin sector, there was no additional symmetry, no spin flip or anything. But another problem where I think our method can probably be applied with some refinement is, for example, to study heating dynamics in Floquet-driven Bose-Hubbard models at strong interactions, where there's a relatively complex heating dynamics because there are these approximately conserved multiple occupancy. And this is just a teaser from some real-time dynamics where we monitor the occupation of kind of the empty side, singly occupied, doubly occupied, triply occupied side as a function of the cycle times. And if you care to look at this plot, there is actually quite some interesting dynamics, which I think is not fully explained also in the literature. And we're trying to make inroads by looking at kind of this Floquet propagator eigenvalue diagram as a function of frequency and analyzing these gaps, but this is work in progress. And another thing where I have been working on before, but where I think at least a variation of our approach could also be useful is for example, long thermalization times in kind of continuous time, so in normal Hamiltonian setting. So I have been involved in work in the Bose-Hubbard model a long time ago, where we saw that in real-time dynamics using ED and also DMRG, time-dependent DMRG, there was some non-thermal steady-state behavior, but people have argued that it could be that these systems ultimately thermalize, but just not on timescales which are accessible to our numerical methods. And there is also some traces in a later paper we looked at the eigenvalue properties, eigenstate properties in these finite systems. And there is actually some hybridization, but only of a few levels in bands which belong to different multiple occupancies. And it could be by adapting our approach of finding avoided level crossings as a function of some parameter, that one could perhaps also be able to estimate kind of thermalization times also in this setting. But this is a bit more sketchy and probably requires more work, but I think there's potential that by carefully and kind of using machines, computer codes to analyze avoided level crossings in a kind of automated way might be a way forward to also understand very slow dynamics in these systems. And of course, one could also look at MBL systems which are driven, where I think there could also be some quantitative heating questions asked. And so I think with the method we outlined here, I think has quite a bit of potential to address heating dynamic problems which are otherwise hard to tackle. And so, yeah, that was it. And I think I thank you for your attention, and I'm ready to answer or try to answer questions if you have some more. So I'm done.
Thank you, Andreas. Now the session is open for questions, so feel free to unmute yourself if you have a question, or you can ask on the chat, and I will read the question for you. We had a couple of questions during the talk, and well, if we don't have any other questions, we thank Andreas for staying up late at night.
Yeah, thank you very much for
taking the time to sharing his work with us. I apologize for the rushed introduction, but I had the dog walking to my in between my legs, someone ringing the bell, my son screaming, and it was a little. But thank you all for joining us, and looking forward to seeing you again next week. Thank you, Andreas. Have a good night.
Thank you very much for being around. Bye.
Bye.